everybody, welcome back. Today we're going to continue our discussion on stoichiometry. So we've already discussed how to convert something, substance A, into something else, substance B, using a mole ratio, which is a comparison between two substances from our balanced chemical equations. We've also added to that the conversion of mass to moles or moles to mass. And today, we're going to add on a calculation involving volume. So when we're talking about volume, we are talking about gases. Our volume calculations are going to refer to those of only gases. And so when we're talking about two gases, we can go from the volume of one gas directly to the volume of another gas, as noted with the blue line here. But when we're talking about some other state of matter, so for example, a solid, if we start with a solid substance and go from the mass of substance A to the volume of substance B, we have to go through moles. So we're going to review both sets of calculations today and talk about how to use stoichiometry when we're dealing with gases. So here we're going to look at a problem where we convert a volume of one gas into a volume of another. Now here we have our stoichiometry roadmap, and going from moles of one thing into moles of another required us to use something called the mole ratio. So going from the volume of one gas into the volume of another is going to require us to use the same ratio. We will talk about this more when we get into the gas laws, but the amount of a gas, or the moles of the gas, is going to be directly related to the volume or the amount of space that it takes up. So the more gas you have, the greater the volume is going to be. And so that ratio is one that we call directly proportional. So we're going to use that same ratio when we solve problems that require us to go from the volume of one gas into the volume of another gas. So here we have a problem that requires us to use that ratio. What volume of oxygen is required to combust 0.875 liters of propane? So take a moment to balance the equation, and then we'll solve the problem. So here we have our balanced equation. How'd you guys do? You should have 1 mole of propane plus 5 moles of oxygen forms 4 moles of water plus 3 moles of carbon dioxide. So now we're going to set up the conversion. The problem is asking us what volume of oxygen is required. So the volume of oxygen is what we're looking for. That's the one we don't know. So that is volume B. Is required to combust 0.875 liters of propane. Okay, that's the one we know. So that is volume A. So we're going to use our mole ratio to convert volume A to volume B. So let's write what we know. We're going to make that a fraction by putting it over 1. 0.875 liters of propane, which is C3H8. So even if you didn't know that was propane because I just told you, you know what everything else is, so you can figure that out. You know O2 is oxygen, you know H2O is water, you know CO2 is carbon dioxide. So we're going to multiply this value, 0.875 liters of propane, by our mole ratio. So we want to get rid of propane. We want liters of propane to be on the bottom. Okay, because once it's on the bottom, it can cancel out. And in our balanced equation, which is what we're using here to get from volume A to volume B, we have 1 mole. Remember, we don't need to write ones in our balanced equation. It's just like in algebra, you don't write a 1 in front of x. And we are converting that to oxygen. Oxygen is our volume B. So we're going to take a look at our balanced equation. We have 5 moles of oxygen. That's going to go on top here. And we can solve. 0.875 liters times 5 is going to give us our answer. So go ahead and take a second to calculate that. All right, you should have gotten 4.38 liters for your answer in the last problem. So now we're going to move on to talk about conversions of mass to volume or volume to mass, depending on what the given value is. So we are going to add on a conversion step here. Just like when we are going from mass of something to moles, we use our molar mass, which is found on the periodic table. And just like when we convert something from moles of some substance A to moles of substance B, we use the mole ratio. We are going to use another conversion factor to go from moles of one thing into volume of some gas. So whenever you're converting between moles and volume, you use this relationship right here. 1 mole of any gas is equal to 22.4 liters at STP. STP is a special set of conditions that we'll be talking more about when we get into the gas laws in a few weeks. But STP stands for standard temperature and pressure. It's a temperature of 273 Kelvin or 0 degrees Celsius and a pressure equal to 1 atmosphere. So whenever a problem says at STP, we can use this relationship to convert moles of a gas into a volume or a volume into moles. So we're going to look at this problem here. How many grams of calcium carbonate must be decomposed to produce CO2 to produce 10 liters of CO2 at STP? So we're going to first write the equation. Calcium carbonate, CaCO3, is decomposing to form calcium oxide and CO2, carbon dioxide. So take a moment to balance that equation, and then we'll set up our conversions. So hopefully you found that it was already balanced and you didn't need to add any coefficients to your equation here. So let's take a look at our problem and see what we're starting with and what we're trying to find. How many grams of calcium carbonate? So we're starting with the mass of calcium carbonate. That means we're trying to find the mass of calcium carbonate. So that's our substance B. Must be decomposed to produce 10 liters of CO2. So here's what we know. 10 liters of CO2 is our substance A. That means we're starting here at volume A, and we're going all the way over to mass of substance B. So we'll start with our given value here, 10 liters. And we're going to put that over 1 and make it a fraction. And then we're going to do our first conversion step. So we are converting liters of CO2, that's substance A, into moles of substance A. So liters of CO2 into moles of CO2 using this relationship over here. 1 mole is equal to 22.4 liters. So we start with liters on the top. That means 22.4 liters is going to go on the bottom of our fraction here, and 1 mole is going to go on top. And I'm going to include CO2 after both of these values because now we're using 2 different substances, and so it's really important so we don't get confused to make sure all of our units and everything matches up correctly. That way, if we aren't sure what the unit should be, we know what's going to cancel out. So liters of CO2 will cancel out here. Now, we are at moles of substance A. That means we need to use our mole ratio to get to substance B. So we're going to take our balanced equation, our coefficients, and we're going to use those to make that mole ratio. Remember, we already had a balanced equation, so it's 1 to 1. 1 mole of CO2 is going to go on the bottom because we want moles of CO2 to cancel out. We want to convert this into calcium carbonate, CaCO3. So 1 mole of CaCO3 on the top. And then we have one more step. Here we are at moles of substance B. We want to get to mass of substance B. Remember, we use our molar mass to do that. So take a moment to calculate the molar mass of calcium carbonate, and then we'll finish the problem. So hopefully you calculated the molar mass of calcium carbonate to be 83 grams. Let me write that a little bit bigger because I don't think it's big enough. 83 grams of calcium carbonate in 1 mole. So we put mole on the bottom, so moles of calcium carbonate cancels out, and we're left with grams of calcium carbonate. That's what we want. So we're going to solve, multiply across the top of our fractions, divide by anything on the bottom, and take a moment to go ahead and solve that. and you should get an answer of 37.1 grams of calcium carbonate. So we just went from volume of substance A all the way to mass of substance B using our stoichiometry roadmap and our new conversion factor of 1 mole equal to 22.4 liters at STP.